Okay, hi everyone. So as Jonathan mentioned, this talk is about Java build tooling. So I guess the motivation for this talk is that the Java language is known to be very fast, easy to use, great IDEs, and then you open up Gradle and everything's opposite. It's not so fast, not so easy to use an IDE. Same IDE, but doesn't work quite as well. So this talk is kind of exploration in what could it be better, and we kind of demonstrates one of my open source projects as an experimental build tool that tries to achieve some of that better, whatever better means here. And you can see that for yourself. So about myself, some of you heard I learned Java in 2004. This was back when you had to take everything out of an array list and cast it before you could use it because generics didn't exist. I've been doing open source projects since 2012, all sorts of JVM stuff, some Scala, some Java, some bytecode, hackery. Fun projects. And my background professionally is developer tools at Dropbox and Databricks. So CI systems, build systems, remote dev environment, multi-cloud. You want a CI system that runs on 2 clouds or 3 clouds. We've done that before. And I'm currently on sabbatical, so not currently employed by anyone. And I'm just traveling and meeting people. So this talk has 4 sections. We'll first kind of dig into what the problem statement is. What's the problem with Java build tools? Could they be better, or is it as good as ever going to get? We look at Mill, which is one of the open source projects I mentioned earlier. We do a lot of open source projects. This one happens to be a build tool. Targets Java, Scala, Kotlin, other JVM languages. And we'll see what improvements it has over the status quo, and one of the key ideas behind Mill, which is the idea of having an object-oriented build kind of configuration, which is very different from how most other build tools work. First, can Java build tools be better? So Maven and Gradle are kind of the foundation of a Java ecosystem, right? It's the reason why no one runs Java-C from the command line. Maven and Gradle do a lot of things for you which are very good. But I think most people would agree that there are parts where they fall short of maybe expectations. So things like the performance is sometimes a bit slow. The ID support for Maven Gradle files isn't as good as ID support for your Java programs, even though it's all JVM stuff. And programming Maven and Gradle to do what you want can be trickier than what you expect. Java is really easy to learn. People learn it in first programming class ever. And then 10 years later, you still have problems like registering their Gradle tasks or something. And then you're like, can it be better? So first, performance. A lot of Java tooling is actually a lot faster than people imagine. And it's only because you have this build tool wrapped around it that it becomes much slower or sluggish is perceived. So, for example, this is a netty code base. I'm using an example here. It's 500K lines of code. It takes about 50 seconds to clean compile in parallel, 10x on my laptop. So I'm going to kick it off here, make this bigger. So here's my, here's netty. I'm just going to copy paste the command and let it run the background. So netty code base, clean compile, go. And okay, so that's a clean, and then it should take about 50 seconds to compile. I'm not going to make you wait for it. So the question is this good or is this bad? And that's a very hard question to answer in isolation, right? 10K lines a second, 50 seconds, not that long, it's not that fast. What is it?
No, you're doing a bunch of things you don't need with Maven or npm install.
Yeah.
You are if you just want to compile and just test it, then it should be verified. Because now you're packaging it and also uploading it to the local Maven repo, which you don't need at all.
Yes, yeah. So that's one thing. So I'll go through that in a second. So another benchmark I ran was the single module compile. So this one's really just compile. You can't compile the whole Maven, a whole netty code base, it will fail. You have to use verify or install, I believe. There's some dependency problems. But with the single module, you see the performance is quite comparable. It's a few thousand lines a second of Java code compiled on your laptop. So is it good or is that not good? Again, you can't really answer. One thing we did is you can compile it without Maven, right? Java-C, everyone has Java-C on their laptops. You can just run Java-C. And the command to run Java-C is kind of long. I shrunk the class path here. It's a bit. I'm not going to make you read it or type it out. But you run Java-C from the command line, and it runs in 1.5 seconds rather than 4.5 seconds. And we can see it here. Okay, so it just finished. The whole clean compile took 50-something seconds, about the same as we saw on the slide. You run Maven clean, Maven compile on a single module. It'll be about 5 seconds, hopefully. 175 source files, 4.5 seconds, more or less what we saw here. And then you run Java C alone. It takes 1.5 seconds, 1.45. So this is a lot faster than Maven. And some of you may know that this is the slowest you could ever get Java C to run. Like, who knows why? You're all JVM developers, right? Some of you are very experienced JVM developers. Why is this the slowest way of running Java C?
It loads the class loads the whole, the class loader loads all the classes from the JDK?
Close. Yeah. So Java C is a Java application, right? And Java applications are slow to warm up, slow to start up, and over time they get fast. So you run it from the command line, it's slow and then never gets fast and exits. You run it again, it's slow and it exits. So this is a really slow way of running Java C. And you're never going to run your web app or Java backend like this. And it's still 3x faster than Maven. So we want to do a kind of better benchmark of the real potential. We can look at this script here I wrote, build bench.java, which basically does the same thing, except it runs Java in memory. So every JDK nowadays has a Java compiler you can use. You probably don't use it, but it's there. And I just put it in a while loop. And I just asked it to print out the time taken, how long it takes to compile, the exact same code that we just compiled using Java C from the command line. So I'm going to just copy paste this, because again, the class path is kind of long. And you'll see that starts off not that fast, but it gets faster over time. Like, this is how you've all been taught the JDKs or JVMs meant to behave, right? The JIT compiler kicks in, we optimize assembly, escape analysis, all that fancy stuff. But basically, after running it, it's faster and faster up to a point. And at some point, it's compiling 29,000 lines of code, same code, in 259 milliseconds. So we've gone from 4.5 seconds using Maven to 1.5 seconds using Java C, worst case, to 0.3 seconds using Java C, like how it should be used as a hot JVM. So compiling Java is not the only thing you do today, but it's this guy's representative of the overhead that your build tools can put on your on the Java platform or Java language, right? Like, literally everything is 15x slower just because we are wrapping it in Maven compared to how it could be. Like, we could be compiling the whole netty code base in 5 seconds on 1 core rather than 50 seconds on 10 cores if we could somehow expose this performance under the hood.
So what's wrong with the Maven daemon? If you replace it MVNV with MVND and combine a clean and install, that will be faster.
Last I tried on this code base, it crashed. I think it's still that's still the problem with Maven D. It's not quite ready yet. That's why it's not the default. Yeah. But so that.
What about the Gradle daemon?
What?
What about the Gradle daemon?
Yeah, we'll see that. We'll see some numbers for that later. So the next thing I'm going to look at is the ID support. So over here, I have an example code base. This is, let me make sure it's the right one. I think it's the other one. Yeah, okay. So this is a Mockito code base. It is built using Gradle. You all know what Mockito is. It's a testing framework. So IntelliJ does have Gradle support, and you can jump to some things, but you can't jump to others. So for example, you jump to, let's say, options. You just can't get a getter and setter. It's a stub, right? There's some way you can set it up to download the sources. I didn't manage to do it today. I failed. So I'm telling you that you can do it. So some things you can jump, some things you can't. And that's kind of common in working with like Gradle and IntelliJ. You tend to get a lot of these stubs where you get getter and setter, or even just a getter. You'll get the Java doc if you set up correctly. I haven't. But this is not.
That's the figment of the Groovy.
It's the same for Kotlin. It's the same for Kotlin. If you want, I can show it to you. I have an example for Kotlin. Yeah, so I mean, this is very different from the way you look at like, any normal Java code, right? Like, you open up a normal Java application, you can jump to anything and you get something useful. You can jump to anything on this like file. You can jump to mock handler. You can jump to serializable. Maybe you hate serializable, but at least there's something there. It'll tell you like this is what serializable is, which is not what you get when you work with Gradle. And I think largely one of the big problems here is you look at these things, they are just getters and setters, right? They are mutable variables. Just because you put them in a getter or setter doesn't make them any less mutable. And they're global variables, because anyone can set them. So the problem here is that Gradle is basically built around global mutable variables, and IDs like IntelliJ can't really help you reason about global mutable variables. They can't tell you where the value came from because someone else somewhere set them. It can't tell you where the value is going because someone's going to read it, but after someone else set them, you don't know who set it to who's reading it. And if you program your normal code base using global mutable variables, you'll have the same problem with your IDE. You'll jump to all these getters and setters, it'll tell you nothing, which is very different from jumping around the method call graph in a normal Java program. That's why people use methods rather than global variables. So that's a performance angle, right? Like it could be better. So this example here is actually Kotlin. The one on the top right is Arrow KT project. It also doesn't help much surprisingly, even though Kotlin is an IntelliJ project or JetBrains project. The IDE is still not as good as Kotlin in the application code or library code. The last thing I'm going to talk about or complain here is the idea of programmability, right? Like you tend to want to avoid putting logic in your build pipeline, but sometimes you need to. Sometimes you have a custom bill of materials, sometimes you have a custom deployment artifact that your infrastructure team wants you to make or something like that. And yeah, you need to do it, and there's no plugin on the internet, so you have to go do it yourself. For this example, I'm just using a straw man requirement, which is take the project line count and save it as a text file you can use at runtime. So it's contrived, it's arbitrary, but you'll do a lot of arbitrary things and it still has to be done, no matter how arbitrary. So you can do this, it's not difficult, but it's surprisingly tricky. So this is like a Maven implementation using the exec Maven plugin. It works, so it's not like it's broken or anything. But there are a lot of edge cases to think about, right? Like, hey, this doesn't work on Windows, so all the Windows people, you have to figure out something else. Your ampersand has to be escaped because it's bash nested in XML, not just normal bash. I'm sure everyone here is going to screw that up because no one remembers XML escaping rules. Generated sources don't work. There are other ways to do it. None of them are pretty. So like, bash script outside of Maven can be done. You run setup.sh and then you run Maven, can be done, but kind of clunky. And script, which is just bash and XML syntax. You can write a custom Maven plugin. All of this is possible, but it's a lot trickier than it should be, given this is like a 30-second new grad interview question. Like, hey, write a program to count the lines in this folder. That you should be able to bang this out with no errors in about 30 to 60 seconds. And with putting it in a build tool like Maven can be a lot more work than 30 to 60 seconds.
I saw some teams who got around this problem by writing it in Java in a test.
I've seen that too. You have one test that you put at the top of the file, make sure it runs before the other test, and it will set up everything you need. It works, but it's also not great.
I would argue with it. Sometimes it does.
Yeah. So, the other side is Gradle. So this is the Kotlin syntax for Gradle. It works. It's cross-platform because it's JVM. It's much less fragile than Bash in some ways, but it has its own problems. So all this manual registration hard-coded paths are very error-prone. So there's actually a bug here which will make your build slower than it needs to be sometimes. Let's give everyone 30 seconds, see if you can spot it. Where's the bug? This is the simplest Gradle custom task you'd ever write, and there's a bug in it, and I'm asking you guys to code review, junior engineer submits this, where's the bug? So I was actually just pointing at it, we are declaring the inputs as the source main folder, and we are only caring about the source main Java folder, which means that if you touch files in your source main template, source main resources, it will unnecessarily rerun this code. For line count, it maybe doesn't matter, it's a small thing, but if you have another task that takes a bit longer, you'll start wondering why your build is getting slow. And if you screw it up the other way, you depend on the wrong folder rather than a superset, your build will become flaky because it won't run when it needs to run. And that's how your build ends up becoming slow and flaky, because even for a simple task, none of you can figure out what's wrong with it. And that's the end, right? Anything more complicated, there's no hope. So that's the kind of problem statement. Maven Gradle, very important, very useful. People use them, and they use them for a reason. But there are lots of ways they can be improved in performance, in IDE support, in programmability, to make it not so error-prone or fragile, hopefully. And that's where the project I've been working on, open source, just the mill build tool, comes in. So this is my own personal project. I've been working on it for a few years, and mill is an open source JVM build tool that tries to address many of these problems. And I think it's quite interesting, that's why I'm sharing it with you guys. It's quite widely used in the Scala folks, but the Java projects not so much. There are a few Java projects using it, but it's not a common thing. A simple mill build looks like this. So unlike Gradle, which is Kotlin or Groovy, mill uses Scala, but hopefully the syntax is straightforward enough you can understand. I have a foo, which is a Java module, I define some IV dependencies, like argpass for J, time leaf, I have a test suite, which is JUnit 4. And I can run like foo.compile, run, test, assembly from the command line. So here, nothing special. This is like really build tool 101 stuff, but it just to show what it looks like. So here's a slightly more involved example of a Spring Boot to do MVC application built using Mill. You can see that this obviously have a lot more dependencies than Java 1 than Hello World. There are two test suites. One is H2 in memory. One is test containers, PostgreSQL with the relevant JDBC driver. And it works. So if I open it up here, let me show it to you live. Sorry, I need to open the right. I have too many pages open. So I go to Spring Boot. I can do mill, what was my command? Test.run background. I can do --watch test.run background. Let me open up a browser tab so I can go to localhost 8084. So this is my to-do MVC application. I can make changes to it. Let's say I change my time leaf templates to instead of capital to-dos, is this the right one? It might not be the right one. But let's say I can do, for example, mill test. See, this should run the test, and it runs. I think I can run the test in the IDE as well. So I can do to-do MVC tests, run it here. You see a test running, homepage loads, and new to-do item. So this is just showing you, you can, Spring Boot example does work. All these dependencies, including like starter and web jars and stuff, it just more or less works. And people often ask, like, what does Mill support? And the answer is it supports most of the open source tooling in the JVM ecosystem. So Mill's very easy to extend, so we just went and extended it to add all this stuff, like you want error-prone support, you want Palantir Java format because Google Java format is deprecated, you want to make a Gradle native image, it's all built in here. And it'll download necessary jars on demand. So it's not like you download a huge build tool. It's just a launcher and downloads the necessary tools as you use them. Languages, frameworks, and so on. Publishing as well. So that's the Mill build tool. Everything we saw here is normal things you can do with Maven or Gradle or Ant or Bazel. So what's interesting about Mill? Why do you care? And I think that's the next section, which is what concrete improvements are we able to show? Yes?
Before we go there, big thing about Maven is that, let's say, IntelliJ understands the Maven class paths. So when I change them, it just picks it up and everything works. How that works with the Mill tool?
I'll show it to you later. Yeah, we'll cover that. So for the improvements that Mill can provide, this is experimental, but just showing off what can be done with JVM tooling. It's a lot faster, it has better ID support, and it's easier to program. And we'll go into each in detail. So in terms of performance, we looked at Netty earlier, and Netty is one of the case studies I've been working on just to see how does Mill actually compare for a real-world project. Netty is not a small project. It's 500,000 lines of code, 50 sub-projects. And what we did is I took the Maven build, which is what they use open source. I just manually ported it to Mill, took like a day and a half. Nowadays it might be faster because we have some automation. And just fixed all the flags and stuff to make sure everything runs, all tests pass on both Maven and Mill. So it's actually quite a complete port, although it doesn't support everything. It doesn't support old operating systems or whatever. But all the tests pass at least on my laptop and on Ubuntu Linux. So if you look at the numbers, Mill is generally significantly faster on a lot of the benchmarks than Maven is. The highlighted one is the benchmark we saw earlier. Parallel clean compile all took about 50 seconds on Maven. And Mill, it takes about 10 seconds to do the same clean compile all. And I can show it to you. Clean. So the first time it runs, it may take a bit longer than 10 seconds because it's a JVM app again. So it might need to warm up. But I've actually gone through the logs and counted all the files it says it's compiling. It's compiling the same number of files in the same submodule layout and everything. And yeah, here it took 14 seconds. If I run it again, it'll take 10. And again, this is still much slower than it should be, right? A Java C compiler should compile everything in 5 seconds on one core. Here we're taking 10 seconds on 10 cores. But it is much faster than what we got from Maven. Yes?
Do
do you do like an interactive mode where you stay in the JVM context and you're allowed to recompile whatever multiple times like SBT? And how does this compare speed-wise with like SBT?
So the way this works is similar to Gradle and Bazel. It keeps the daemon in the background. You don't need to go into a console like SBT. You just run it and it will spawn the daemon as necessary. If daemon dies, it'll spawn it again and it'll reload the config and stuff as necessary. So it's very similar to how Gradle is architected. Just somehow we have lower overhead for unclear reasons to me.
At least less fussy.
Yeah. So I demonstrate the parallel clean compile benchmark, but all the different benchmarks. For example, you do nothing, Maven takes a while, and Mill takes less of a while.
So that one is the when you like run the same Maven call without calling clean.
Yeah, just like there's nothing to do, right?
Because that's what you're supposed to do. Like nobody should call clean ever.
Yeah. No, for no op compile, that is when you compile everything. You don't clean and compile again. So nothing should happen, right? It should be instant. There's nothing to do. You already compiled everything. And for Mill, it's pretty fast. We quickly realize there's nothing to do and exit. We do have to check all the hashes and stuff to make sure the files haven't changed. Maven does all the same thing, but there's a lot more overhead like spawning the JVM. Some of it goes away in Maven D if that will land. But there's still a lot more overhead loading class loaders and stuff in Maven than there is in Mill. The other example we did was Gradle. We used Mockito again as an example. Took the Mockito Gradle build, ported to a Mill build manually. Now there's automation. Back then there wasn't. And the numbers are less dramatic, but it's still like maybe 3 to 4x speed up for compiles compared to Gradle. So this, even though Gradle has the same like hot daemon thing that Mill does, I don't actually know where the Gradle overhead is. I haven't managed to figure that out. But it's also still not as fast as the Java C compiler should be. So there's definitely a lot of room to improve both for Mill and for Gradle. So compile's not everything. There's some other interesting things like watch and rerun I didn't show. Mill does selective test execution, so you can do things like check out main, take a snapshot, check out your pull request branch, ask the build tool what changed. Because the build tool knows who depends on who, right? You should be able to say, hey, this code changed, this code is part of this module, that module is downstream of this module, that test suite belongs to that module. So of course you should be able to do this, and Mill is quite easy. You can even ask it, tell me why this test changed, and it'll say, okay, you touch this file, it's in test repo source shoot, in test repo in resources and test. And you run it, it'll only run that test and won't run all the others. Very handy in big code bases for CI. Assembly jars can be made incrementally. I don't know why other build tools don't do it. Like assembly jars are jars, jars are zips. Zips can be updated efficiently by opening them up and taking files up, putting them in. Java even has a Java NIO file, zip file system that lets you do that. And that's what Mill does, right? You compile it, Mill will just hey, this file's changed, I'll take out the old one, put in the new one. So incrementally making Spark submit assemblies is much faster in Mill. The Chrome profile is interesting. So every Chrome browser on all your laptops has a profile visualizer. I don't know who knows this. Anyone has used this before? 1 person? 3 people? So if I open up my Netty code base, every time I run a command, Mill generates this Mill Chrome profile.json file. So on its own, the file is not particularly readable, but it's a standard Chrome profile format that you can just dump into your Chrome browser, which you already have. And it just tells you where's my 10 seconds clean compiling the whole Netty code base going. And you get this for free, right? You don't need to go pay for Gradle Enterprise and go set up a self-hosted Gradle Enterprise server and upload your build scans and everything. Just take the JSON file, dump into Chrome, and you can see at the start, my CPUs are well used, gets bottlenecked on common compile. After common compile finishes, other things kick off, gets bottlenecked on buffer compile. And this is very helpful to tell you, people often ask, why is my build slow? And here you can say, hey, here's why your build's slow. Maybe you should break up your common module. Maybe microbench over here on the right is taking too long. It's a long pull. Maybe you should go break that up into multiple smaller benchmarks to compile faster. And again, this is not only for compile, but your tests, your packages all generate, packaging, deployments all generate this profile every command. So it's very handy to just figure out why your build tool is doing what it's doing and taking the time it's taking. So that's a performance angle where none of the things you showed here are particularly magical. It's just you're creating a JSON file here, opening a zip there. But the net effect is that it just makes it a lot easier and faster to work with your JVM projects and easier to optimize them so you don't get bottlenecked on your build tool. The next thing we're going to look at is ID support. So I guess the interesting thing here is if you open up Gradle and mill for Mockito side by side. So let's do that. So here's one. Here's the other. Let's see which one's which. Okay, so here is error prone dot Gradle. So on the left is the mill build for the Mockito error prone submodule. On the right is the Gradle build for the Mockito error prone submodule. Mockito has 20 modules. This is just one of them that happens to be easy to explain. So the first thing you realize is that you look about the same, which is expected because these files need these flags to run. These files need these dependencies. So whether you're using Maven or Gradle or Mill or Bazel, you just need to configure that. That's unavoidable. Where things diverge a bit is ID support. So like you ask for, you ask for the Java doc for JVM, you get something. You actually don't get anything here because I haven't set up the sources. But you jump to it, you get these getters and setters that don't really tell you much. For example, you can't just like grep for it and see where it's being used because it could be used anywhere in the whole Gradle code base, both Gradle upstream as well as in your build.gradle files. For Mill, the syntax is a bit different. It uses this def fork args instead of JVM args plus equals. But one thing to notice is your ID already understands this. It's an override. So Mill uses overrides rather than mutation, and that helps a lot for the IDE. So Mill knows that fork args overrides these three implementations. For example, you go to run module. You can see the value before you overrode it. You can see the Java doc or Scala doc because it's Scala syntax. And you can immediately start grepping for things. I can say that, okay, fork args is used in runner. Runner is used in run background task, this deprecated thing we ignore. Run fork task. Run fork task is used in run. So this gives you kind of an insight into not just what the documentation is, what type signature is, but how do these build configurations actually end up affecting the thing I want? How did I change fork args here? How does it go into my run method here or run task here? Which is not important if everything's going correctly, but when things go wrong, then this gives you kind of an escape hatch to figure out, okay, there's no docs, the website's out of date maybe, or it's a custom plugin that's unmaintained, but at least I can go into my IDE and figure out what's happening, how my values are being passed around my build graph. I can go the other way too, right? Just now I showed you the downstream exploration, but let's say I don't know what this final main class is. How is it computed? I can jump to it. Okay, no documentation, that's bad, but I can look at the implementation. I can jump to its upstream tasks. And okay, final main class opt is either the configured main class or the all local main class. So that's all local main classes. I can jump to that too. So I guess the interesting thing here is not that it's special. The interesting thing here is that this is what you guys already do day to day in your application code base. Like no one writes perfect docs. All your Java doc or Scala doc is always missing or incomplete or out of date. And nevertheless, you still can explore your code base because your IDE helps you figure out what's going on, what values are going where, who's calling who, and you can fix things even without the perfect documentation or perfect abstraction set up for you. And that's what Mill brings to your build tool. So in Gradle, you jump to this, you don't know what it does, you get stuck, you have Google, or you open up GitHub Gradle code base and open up the Gradle code base and start grepping for things. Whereas in Mill, you can always go into your build pipelines and figure out what's happening. At least to some extent, much more so than you can in the other build tools. So that's ID support angle, where I think Mill is pretty interesting. Last angle I'm going to look at is programmability. Yes?
Could you explain how the IDE picks up the class path? How it understands, say, I add some dependencies to the mill?
There's a button here where you can reload it and it picks it up. So you see this thing called BSP. IntelliJ exposes the build server protocol that Bazel, Mill, SBT, and some other build tools also support. It's trying to be like the build tool equivalent of LSP from the JetBrains folks. And Mill supports that protocol. So we spawn the JSON RPC server, and IntelliJ will make JSON RPCs to the Mill process and ask it, what's your JVM args, what's your environment variables, what's your Maven dependencies, and we'll just give them the metadata, and they'll populate all this stuff here. So you see on the right here, all this is populated by IntelliJ over this protocol.
How IntelliJ knows that it is there? Like, do you generate the ID project files? If you just start IntelliJ, it will there is some magic under the hood where it will know where is the build server?
Both. So there are two options. You can either generate IDE project files, so Mill can, you guys may know that this IDEA folder that IntelliJ has, Mill can just generate XML for you, and IntelliJ will load it and end of story. The other thing is, if you don't have anything and you open up a project with a .mil file, IntelliJ knows that it's .mil because I asked the JetBrains folks and they put it in.
Oh,
So
okay.
they were nice. Yeah.
It's not even a plugin.
It's part of the Scala plugin because we use the Scala syntax. So I just hey, I'm using .mil. Can you support it? And it's if .mil, then it's a mil project, and then it'll connect to the server and everything using their standard protocol. Okay, so okay, back to the slides. So talking about programmability. I guess the first thing here is that you often don't need to program Mill or find as many plugins for Mill as other build tools. Like there's so much more stuff is built in, like assembly jars and everything are just built in. You can just use them. Everyone wants to deploy something to run, right? So I want to do it, so I just built it in. But beyond that, any big project often ends up needing customizations. So the interesting thing about Mill is that you don't have this like plugin like intermediary between the logic you want and your build. Like you can just take the logic you want and run it yourself, and you'll see what that means. So time for some coding. If you go to here, this is my custom Java Hello World Java program. This is the minimal Mill build for Java. You'll notice there's nothing there, which is what you'd expect because Mill kind of follows a convention over configuration thing that Maven and other people pioneered. So you want all the defaults? Well, here are all the defaults, and you only need to customize the things that are actually custom. So let's say I want to go back to my count the lines of code in this project requirement, right, and add it to a resource file. How do I do that in Mill? So Mill uses Scala syntax rather than Kotlin syntax, but it shouldn't be too complicated. So Scala uses def to define a method. I can say def line count is a task, and I can call other methods. For example, you're not sure which source method you want to call, you can ask IntelliJ and you get ID support. You can say like, on all the source files, for each file, I want to read the lines of that file, take the size of it, or length, whatever. Then you say file.path, sorry, and I sum them up. So this is how you define the line count custom task in Mill. It's a lot lighter weight than Maven or Gradle, and you get ID support and other nice things. So now that I've done this, I can do Mill show foo.line_count in the terminal. Takes a moment to compile this code. Okay, 17, this is how many lines I have in this example file. I can do Mill inspect foo.line_count. You'll see that things like we automatically capture Java doc for you, which is very convenient. You don't need to go copy paste it to a string somewhere.
When you run this, will it look into the bytecode, or do you have like another mechanism to get like data out of your code?
All of the above. Yeah, so the implementation is a bit complicated. Like we have a compiler plugin to grab the Java doc. So some of the invalidation is done by bytecode analysis, so you know that you call this method, and for example, like this foo.all source files being captured here, you can't do that for a normal method, right? When you call a method, you can't just say, hey, what method does this method call? But we have some compiler plugin that does that for you. And it works 99% of the time. Like 1% of the time, you need to do something special to work around this hackery. But 99% of the time, it more or less just you call methods and it kind of just works. So here's a line count task. We haven't added it to resources yet. So the way you do that in Mill is via overrides. So I can say override def resources. Again, you get ID support. You don't know which resources you want to override. There's a bunch of them. Compile resources, doc resources. I'm going to just use normal resources. I'm going to say super resources plus like reference. This is a path reference to this task.destination folder. I'll explain that in a moment. And I'm going to write to this task.destination folder line count.txt and just call the line count and stringify it. So what's this task destination folder? Basically in Mill, every task gets its own folder to put stuff in. And this is very handy because it makes sure that no tasks will ever collide and stomp over each other's files, which is a very common problem in other build tools. Like, hey, you're using the lint path, I'm using the lint path too, and then both linters like break each other. So in Mill, every task gets its own folder. If I do Mill show foo.resources now, you'll see that my override for resources it returns the resource path, which is both the original resource folder here, as well as this out/foo/resources.dest. So this is the destination folder every task gets that's unique to that task. So we make sure you don't collide. Now I can look inside this out/foo/resource.dest, see my line count.txt, value 17. I can do mil foo.run now. And you see it's able to load this at runtime using your standard like class loader, resource as stream, read all standard Java APIs. So I think this is quite interesting. This is, I think, a lot lighter way to configure your custom logic than Maven or Gradle. You're not configuring like input files or output files or setting hard-coded paths on disk and hoping they line up. You kind of just call methods and override and call superend when necessary. And it works as you'd expect. Like you all learned override in Super 15, 20 years ago, maybe. At least I did. And it works the same way here as it does in Java 101. Let's take this one step further. Let's say I want to render my line count as a HTML file. Just again, another straw man contrived example. So mil doesn't have like timeleaf built in. You can't do org.timeleaf. It'll yell at you. Like you try to do foo.run here, it'll yell at you here as well. So what do? So what mil does is it has a syntax for easily importing Maven libraries or IV libraries artifacts from your build file. You can say import $iv with backticks, and then you can say org.timeleaf, let me make sure I spell this correctly, and add a version. And now, if I run this, you'll see that I haven't started using it yet, but now this compiles. And if I reload my IDE by asking IntelliJ to reload the project, you'll see that I'm now able to see timeleaf in my libraries where previously it was not. So I can say timeleaf context maybe, template engine. And we are almost done here with this example. So I want to add my HTML line count generation task that renders my HTML at compile time. I already imported timeleaf into my build, which I didn't have before. I can define a new task, HTML snippet, that says, let's say, I create a new timeleaf context. I set the variable like line count to line count, and then I need to do new template engine dot process. I'm going to pass in the context, and I'm going to copy and paste the template from the slides because it's a bit finicky to type out the timeleaf template live. So where's my timeleaf template? Here's my timeleaf template. Line count. And then I replace this resources with my HTML snippet and have to call it. So now if I do mil foo.run, you'll see it renders my HTML at build time using timeleaf. I can look at the files on disk, for example, cat out/foo HTML snippet of JSON. You can see you can see the file, the data being rendered as part of my like cache JSON files. And that's it. So this is how I use like overrides, super, and method calls to configure my build while still getting things like caching and invalidation and parallelism that you want in your build tool. I think what's the most interesting thing about this part is that you get caching, invalidation, and parallelism, and dependency tracking and all that. But you look at the code, there is no code related to those concepts. I'm not registering input-output files, do lasts, depends-ons. I'm not like creating threads or executors or futures or locks or computing cache keys and invalidating cache files, deleting them. All that gets handled by the build tool. So you're basically writing pure build logic, whatever you want your build to do here. And then you just ignore all the rest, and it more or less does what you want for you. So I think that's what's most interesting about this way of like extending your build tool. I guess the other thing to mention here is that we didn't need any plugins for this. There's no Maven, there's no mil line count plugin. There is no mil HTML rendering timeleaf plugin. And we didn't need it. Like, let's say we already know how to count lines on this because we are programmers. We already know how to use like timeleaf. You want to use other templating engines, you can as well. Just import them. You just import them and can use them directly rather than having to go through this intermediary of a half-maintained GitHub repo that no one looked at for the last 6 years. So I guess just to move on, comparing the mil code to the Maven code, I mean, the first thing I think is notable is they really contain the same build logic, so it's not like we're doing anything magic here. Someone has to say that we're going to count the lines of code recursively within the source files and add it all to a line count.txt, so that code has to be there. But the other thing that's interesting is, like, just because we added we took the bash snippet and wrapped in a bunch of XML doesn't make the bash snippet any less kind of fragile or bashy. It's still a bash snippet, still kind of dangerous, maybe even more dangerous now because of escaping. And like, you want to have declarative builds, but sometimes you really need some logic. And you look at the Netty code base, it has some custom code calling GCC or Clang. Look at the Mockito code base, it has some custom logic mangling class files in order for it to work. So these things need to be done. And even though your larger build tool may be declarative, you still need some way to manage this kind of complexity, which may be some imperative code. And it's still imperative code, but at least you get ID support and type checking and other nice things, which you don't really get in your bash snippets you write as part of your Maven scripts. Compared with Gradle, again, the business logic or build logic is about the same between the two. And I guess the interesting thing here is that the build logic in the Gradle snippet is not the part that people will get wrong. And I'm sure all of you were code reviewing this logic just now, and none of you found any bugs because it weren't any. It's correct. And you asked a new grad to write it, it's correct. But is all this input.files, output.files do last, or should you use do first sometimes? Or this task.name depends on? And all of that, that's the part that you will probably screw up. The build logic is actually not so complicated, and it's quite easy to write and quite easy to read. So what Mill does is that it tries to automate as much as possible so you don't need to have this ceremony before and after. And in doing so, I think it makes it a lot less error prone. So with Gradle, it's probably correct not to write too much code in your Gradle script because you'll make a big mess of all this stuff around your build logic. But without needing to write this stuff, it's actually quite easy to customize the Mill build to do what you want. Like, you look at the code on the right, I would dare say it's not too complicated and it's not too hard to get right. So that's the last angle of why I think Mill is interesting and what it improves upon the existing build tools. Yeah, so back to the slides, the last thing is this idea of object-oriented builds. You keep seeing this extends, def, super, objects, class. And I think that's one of the biggest things that sets Mill apart from the other build tools. Like, other build tools can implement a daemon. That's like not rocket science. Other build tools can keep track of what files you're writing and reading. That's also not rocket science. But what makes Mill interesting here is, like, when you say object foo extends Java module, you're literally inheriting methods from a class. So in Mill, these methods become your tasks, and the method call graph becomes your build task graph. So this is slightly simplified, but you have sources that gets called by compile, gets called by class path together with resources gets called by assembly. And because it's just methods, right? Like, you all know how methods work. So when I define a new method, sure, the syntax is different. You use def to define it. But when I define a new method and call another method, or when I override the method and call a super and call another method, you actually know how all this stuff works. You know how this splices the method call graph because you've been using defs, method definitions and calls and supers and overrides for decades. And the interesting thing is, once Mill has this graph, Mill can say, for example, compile and line count can run in parallel. They don't depend on each other. The green thing here, assembly, needs both of them to finish before it can run. So schedule that last only after the first two complete successfully. Mill can give each method or task its own cache JSON on disk, so that does automatically. As well, for both JSON is the metadata that you return, so like this returns the sum, and so the sum becomes put in the JSON file. But these like task.dest files that I create get put in the dest folder. So compile gets its destination folder, assembly gets its destination folder. They'll never collide. It's very convenient. And okay, the last thing a Mill does is invalidation. So let's say you touch the resource folder. Mill knows the resource folder super resources because you overrode it. Mill knows that you call super resources and resource in assembly, so it just does a breadth first search. Mill knows that to invalidate assembly, you need to delete the assembly JSON assembly.dest folder because of the standardization of the paths on disk. And similarly, Mill knows that you don't need to recompile or re-evaluate the line count, and it knows where to get the metadata and data from, right? Like, compile always is in the same place according to the name of the method and name of the object. Line count will always be in the same place. So Mill knows how to pick this stuff up all for you. And again, you don't need to do this as a build author. You just say, here's my build logic, and Mill will take care of dependency tracking, parallelism, caching, invalidation, all for you, without you having to do it yourself and possibly screw it up, which happens a lot in other build tools. So So that's the idea of object-oriented builds, where instead of having these kind of like registration, global mutable variable system, you define a bunch of objects and inherit from classes and define methods. And extends, overrides, super all work as you expect. They all work as IntelliJ and VS Code expect, so IntelliJ can jump around, doesn't even know it's a special .mil file. And mil just handles everything else for you, which the consequence is the performance is always good because you won't be forgetting to parallelize the tasks or opt into caching. You don't need to clean as often because people won't screw up the caching as much as they do in other build tools where you have to do everything manually and someone's bound to make a mistake. And it makes life easier for everyone. It makes life easier for the build maintainer who's working on this project, but also like the plugin maintainer who can very easily create a plugin for something that other people can use. So earlier we saw the integrations we had for all the linters, all the different packaging tools, Gradle native image, and they were very easy to create. So I just when I created them because as you saw earlier, it's very easy to create custom tasks and custom build pipelines in Mil. And so I think that's coming on to a last slide. So I guess there are two main thrusts here. One is there's a lot of stuff that the existing build tools really should do and aren't doing. Things like making Maven D like production ready as a default, selective testing, automatically generating profiles. Like, why do I need to have a Gradle enterprise server just to see what tasks are taking a lot of time in my build? That's a bit silly. Just give me the data to load into Chrome. So Maven and Gradle and other build tools really should just do these things. They're low-hanging fruit, don't require any big changes, and will make people's lives better. And on the other hand, I think the other thrust is that I think Mil is actually pretty cool. Like these object-oriented builds are a new way of looking at your build that's very different from the XML or global mutable variables that you're maybe used to in Gradle. And apart from being of academic interest, it's also gives some real like concrete improvements, right? Like the ID support we showed earlier, exploring your build graph is something you just cannot do with the global variables in Gradle. Yeah, so I think this is quite interesting. Hopefully you guys, if you're interested, can try it out. If you are bored waiting for a Gradle or Maven build one day, or particularly frustrated with the Gradle custom task, and see if Mil is interesting to you. Yeah, the project link is below. All the examples here are executable and integration tested, so you can download the zip and try it out without any installation. Yeah, and I guess I can take questions.